All right, today we're going to dive into one of the most powerful and honestly kind of magical ideas in all of statistics. It's called the Central Limit Theorem. And really, it's a concept that finds perfect order in what looks like total chaos. And it all kicks off with one big question.
So here's the puzzle, right? How can we possibly make any reliable predictions about a huge group of things when the data from that group is just all over the place? When it doesn't fit into a nice, clean bell curve. It seems like it should be impossible, but the answer is pretty mind-blowing.
So the first thing we just have to accept is that data in the real world is messy. It's almost never the perfect, tidy pattern you see in a textbook. Let's look at a couple of real-world examples. Imagine for a second that you're measuring the width of turtle shells. It's totally possible that any width between, say, 2 and 6 inches is equally likely. What you get is this flat, uniform distribution. It looks like a rectangle, which is about as far from a bell curve as you can possibly get.
Or think about this one, the number of pets people have in a city. You're going to have a ton of families with 0, 1, or 2 pets. But, very, very few families are going to have 8 or 9. So the data is all piled up on one side. It's heavily skewed. Another totally unpredictable, non-normal pattern.
So this is the problem we're facing. If our original data looks this weird, how could we ever confidently say anything about the average turtle shell width or the average number of pets? It really does feel like we're stuck. But we're not.
The secret, as it turns out, is in what I like to call the magic of averages. The whole idea is that when you start averaging a bunch of random numbers, the really high values and the really low values, they just tend to cancel each other out. Let's actually run an experiment with our turtle population to see exactly how this works.
The process here is super simple. We're going to reach into our flat turtle population, grab a few at random, calculate their average shell width, and then we'll put a single dot on a brand new graph to represent that one average. Then we're just going to do that again and again, thousands of times over.
All right, so we're starting really small with a sample size of just 2 turtles. And when we plot the average width for each pair, this new graph, well, it still looks pretty random. There's no obvious pattern here just yet. But watch what happens when we increase our sample size to 5 turtles at a time. Do you see that? A shape is actually starting to form. The averages are beginning to pile up right there in the middle. It's getting interesting. And now for the big reveal. When we get to a sample size of 30 turtles, something absolutely incredible happens. The distribution of our sample averages turns into this almost perfect, beautiful bell curve. Just think about that for a second. We started with data that was completely flat, but the averages of its samples created this predictable, normal distribution.
Okay, that is just incredible. But you might be thinking, was that just a fluke with the turtle data? It's a fair question. So let's test this whole thing again with our other, much weirder data set, that really skewed distribution of pets per family. As you'd probably expect, when we take tiny samples of just 2 families, the distribution of their average pet ownership is still pretty skewed, just like the original population was. No surprise there. But look at this. Just by bumping the sample size up to 10 families, that heavy skew is already starting to disappear. The whole distribution is becoming way more balanced, and it's shifting toward the center. And then, at a sample size of 30 families, there it is, again, the exact same bell shape. This is the amazing part, you guys. We started with 2 totally different, completely non-normal populations. And this process of averaging their samples gave us the exact same predictable pattern both times. So this isn't magic, it's mathematics. What we've just seen happen twice has a name, and it is, without a doubt, a cornerstone of modern statistics. This is the Central Limit Theorem. It's the formal rule that says exactly what we just watched happen. No matter how weird or messy or skewed your original population data is, the distribution of the averages from its samples will always be a normal bell-shaped curve, as long as your sample size is big enough. And the theorem tells us 2 other incredibly useful things. First, the peak of that new bell curve, its center, is going to be the true average of the entire original population. And second, the spread of that curve, how wide or narrow it is, totally depends on our sample size, n. The bigger our sample size gets, the narrower and more precise that curve becomes. That's exactly why the bell shape got so much tighter when we went from 5 to 30 turtles. Now, all of this naturally leads to a very practical question. The theorem says it works if the sample size is large enough.
But what does that actually mean? How large is large enough?
Well, while it's not some universal law written in stone, the most common magic number you'll hear in statistics is 30. A sample size of 30 is the generally accepted rule of thumb for the central limit theorem to kick in and work its magic.
Of course, there's some nuance here. If your starting population is already pretty balanced and symmetric, kind of like our flat turtle data, you might see that bell shape start to emerge with a sample size as small as 15. But for really skewed data, like the pet example, 30 is a much safer bet. And for something that's extremely skewed, you might need to go even higher, maybe to 40 or more, just to be sure. Okay, so we've seen this really cool statistical phenomenon, but why is it considered one of the most important ideas ever? What's the real-world payoff here?
To put it as simply as possible, the central limit theorem is the reason we can make confident, educated guesses about huge unknown populations. All the turtles, all the pet owners, based on just a small, easy-to-manage sample. It is the absolute bedrock of statistical inference. This slide really says it all. Without this theorem, we're completely stuck. We can take a sample from a weird population, sure, but we have no idea how its average relates to the true average of everything. But with the theorem, we're empowered. We know for a fact that our sample average comes from a predictable bell curve, and that lets us make incredibly powerful predictions about the entire population from just one small sample. So we'll end on this thought. The central limit theorem proves that a predictable, even beautiful sense of order can rise up from what looks like complete and utter randomness. And it kind of makes you wonder, doesn't it? What other profound, hidden patterns are just sitting there, waiting to be discovered in the data that surrounds us every single day?